The general analytical solution to the complex three-body problem has not yet been found. The five special Lagrange points represent known particular exact solutions to this problem. Determining the complex motions of four or more celestial bodies is called the n-body problem. The discovery of the distant planet Neptune became the ultimate proof of the validity of classical Newtonian mechanics in our system.
All right, let's dive right into one of the most profound and enduring challenges in all of physics, the n-body problem. At its heart, this is about a very simple question. If you have a group of objects pulling on each other with gravity, can you predict where they're all going to go? It's a question that has really defined celestial mechanics for centuries, all the way back to Newton himself.
You see, when you have just two bodies, say the Earth orbiting the Sun, Newton's laws are perfect. They're elegant, you can write down a precise formula that describes their dance for all time. But the moment you add just one more body to the mix, everything changes. The whole system becomes profoundly complex, even chaotic. This is the famous three-body problem. And here's the catch. There is no general, one-size-fits-all formula to solve it. It's been a central mathematical roadblock ever since the 17th century.
So here's our roadmap for this discussion. We'll start by digging into why this problem is so notoriously difficult, why we call it unsolvable. Then we'll explore some incredible exceptions, these little islands of stability where things are predictable. From there, we'll scale up to the even bigger n-body challenge, and I'll share an amazing story of a mathematical triumph. Finally, we'll see how this centuries-old problem has a massive legacy in today's astrophysics.
So Section 1, the unsolvable problem. And the subtitle says it all. Why 3 is a crowd? When we say there's no general solution, what that really means is that the system is often chaotic. It has a sensitive dependence on its initial conditions. So if you change the starting position of one body by a microscopic amount, its future path can become wildly different. Because of this, we can't rely on a simple formula. We have to use powerful computers to calculate the motion step by step, or we have to hunt for very specific stable special cases.
Now, this leads to a really crucial question. If the general problem is such a chaotic mess, are there any configurations at all that are stable and predictable? And the answer, remarkably, is yes. And these special cases aren't just mathematical curiosities, they represent real, physically important points of stability right here in our own solar system.
These exceptions are known as the Lagrange points. Essentially, they are 5 specific locations in a system of 2 massive bodies where a third, much smaller object can maintain a perfectly stable position. Think of them as gravitational sweet spots, where all the forces are in perfect equilibrium. They are true islands of stability.
The first 3 of these points, L1, L2, and L3, were discovered by the great mathematician Leonhard Euler. They're called collinear because they all lie on the straight line that connects the 2 massive bodies. So imagine a line running from the Sun right through the Earth. L1 sits between them. L2 is on the far side of the Earth, and L3 is on the far side of the Sun, opposite the Earth. At these precise points, the gravitational pulls from the 2 big bodies perfectly balance out the centrifugal force of the orbit.
And this isn't just theory. The L2 point of the Earth-Sun system is a prime example of this in action. It's exactly where we've placed the James Webb Space Telescope. From this position, about 1.5 million kilometers from us, the telescope can keep the Sun, Earth, and Moon all behind its sun shield. This is critical for keeping it cold. And because it's in a gravitationally stable parking spot, the telescope needs very little fuel to maintain its orbit.
After Euler's discovery, Joseph Louis Lagrange himself found 2 more solutions in 1772. These are L4 and L5, and they're different. They're not on that straight line. Instead, they're located at the third point of 2 equilateral triangles, with the 2 massive bodies forming the other 2 points. So, in the Sun-Jupiter system, for example, L4 and L5 form these 2 perfect triangles.
What's fascinating is that the entire configuration, the Sun, Jupiter, and any objects at L4 and L5 rotate together as if it were a single solid object. Now, for over a century, this was just seen as a theoretical solution. But then, in the 20th century, astronomers discovered huge clusters of asteroids, which we call the Trojans and the Greeks, occupying these exact L4 and L5 points in Jupiter's orbit. It was an absolutely stunning confirmation of Lagrange's theory. Okay, so 3 bodies are a challenge. But what about our solar system, with its 8 planets and countless other objects? This is the full-blown n-body problem, and the complexity just grows exponentially. To have any hope of tackling this, astronomers had to develop a very powerful mathematical tool.
This tool is called the method of perturbations. The idea is brilliant in its simplicity. You start by calculating the simple two-body elliptical orbit of a planet around the Sun. Then, you systematically add in all the small gravitational influences, the perturbations, from every other body in the system. For example, Jupiter's gravity gives Earth a tiny tug. Saturn gives it another, even smaller tug. By carefully adding up all of these small corrections, you can get a remarkably accurate approximation of a planet's true path.
And this powerful method led directly to one of the greatest intellectual achievements in the history of science, the discovery of a brand new planet, not through a telescope, but with pure mathematics. The whole story starts with the planet Uranus. After its discovery, astronomers carefully calculated its orbit using this method of perturbations, accounting for all the known planets. But there was a problem. The observed position of Uranus was consistently off from its predicted path. It was clear that some unknown force was at play. This anomaly led to a bold hypothesis. There had to be an unknown, more distant planet that was gravitationally perturbing Uranus. So two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, completely independently, set out to solve the inverse problem. They used the observed wobbles in Uranus's orbit to calculate the mass and location of this hypothetical planet. Le Verrier then sent his coordinates to the German astronomer Johann Galle,
and the result was a spectacular triumph. On September 23, 1846, Galle pointed his telescope to the exact coordinates Le Verrier had provided, and he found the new planet, Neptune, within just 1 degree of its predicted position. This wasn't luck. It was the direct result of rigorous mathematical deduction.
This discovery, made on the tip of a pen, was so much more than just finding a new world. It served as the ultimate proof of Newton's laws of mechanics across the vast scales of our solar system. It was a true testament to the predictive power of science.
And that legacy, which began with an 18th century math problem and was confirmed by a 19th century discovery, remains absolutely central to how we explore the cosmos today.
I mean, these principles are truly foundational. We place solar observatories at L1 for an uninterrupted view of the Sun. We use L2 for deep space telescopes like James Webb. We understand the dynamics of asteroid groups like the Trojans at Jupiter's L4 and L5 points. And today we use massive supercomputers to run n-body simulations for everything from predicting the long-term stability of our own solar system to modeling the collisions of entire galaxies.
And yet, after all this progress, the fundamental n-body problem in its general form remains analytically unsolved. We've mastered its approximations to discover planets and to position our most advanced instruments, but as we probe the outer reaches of our solar system, as we analyze the complex dynamics of exoplanetary systems, and as we model the universe's large-scale structure, the question remains, what future discoveries are out there waiting for those who can further refine our understanding of this elegant, chaotic, and absolutely foundational problem of celestial mechanics?
Thank you, friends. Strive for understanding and become wiser. See you soon.